Next topic is bifringence or double refraction. Up to this point, we are aware that if we have an interface between two medium, this is medium number 1 and this is medium number 2. So this is the interface between these two mediums, and a ray of light is incident on this interface. Then at interface, it will undergo refraction. A part of it will enter into the second medium, and this process is known as refraction. So in this ordinary refraction, when one ray of light is incident on the interface separating two mediums, a part of it will enter into the another medium and a part of it will be reflected. This is known as ordinary refraction, and if this angle is I and this angle is suppose R, then it follows Snell's law, and here I am assuming refractive index of first medium is N1 and refractive index of second medium is N2. So according to Snell's law, N1 sin I will be equal to N2 sin R. So in refraction, for one ray of light, there will be one refracted ray. But in nature, there are many anisotropic mediums on which if ray of light is incident, then for one incident ray of light, we will have two refracted rays. These anisotropic mediums are known as doubly refracting mediums. So, and the simple example of doubly refracting mediums are calcite, quartz, topaz, tourmaline. So if I consider the principal section of a calcite crystal, so I am assuming this is an anisotropic medium which is acting as doubly refracting medium, and a ray of light is incident on this, and as a result of this incidence, you will have two refracted rays. In one ray, you will find out electric vectors are parallel to plane of incidence, and in another, electric vectors will be perpendicular to plane of incidence. And out of these two refracted rays, one is known as E ray and another is known as O ray. So basically, if unpolarized light is incident on a doubly refracting medium, then in this doubly refracting medium there will be two refracted rays corresponding to one incident light, and one ray is known as E ray or extraordinary ray, another is known as O ray or ordinary ray. So the phenomena due to which for one incident ray of light, we will have two refracted rays, that phenomena is known as double refraction, and the crystals which exhibit this type of properties, or the materials which exhibit this double refraction, they are known as doubly refracting mediums, and the common examples are calcite, quartz, topaz, tourmaline. These are the common example of doubly refracting mediums. These doubly refracting mediums or this phenomena can be easily observed if we have a calcite crystal like this. Here we have a calcite crystal. So first we will take a plain paper. On this plain paper we will draw a point. And then on this paper we will place a doubly refracting medium. Suppose this is the axis of this double refracting mediums. So you will find out corresponding to this one point on the white paper, when we are placing double refracting medium of crystal on this, then corresponding to this one point we will observe 2 points. One is corresponding to O ray, another is corresponding to E ray. So this is the simplest method in which we can observe the double refraction. And if we rotate this crystal, then you will find out that this E ray will rotate around the O ray. This point corresponding to O ray, this will be fixed, and the point corresponding to E ray, this will rotate along with the rotation of this crystal. So this is the simplest way in which we can observe double refraction. Now the crystals which are exhibiting this double refraction, they are known as doubly refracting mediums, and this phenomena in which for one ray of light we have two refracted rays, this is known as double refraction. These doubly refracting crystals, they can be classified into two type of doubly refracting crystals. One is known as uniaxial crystal, and another is known as biaxial crystal. Biaxial crystals. One is known as uniaxial crystal and another is known as biaxial crystal. Uniaxial crystal are those doubly refracting crystals which have one optic axis, and biaxial crystals are those crystals which have two optic axes. Example of uniaxial crystal is calcite, quartz, etc. And example of biaxial crystal is topaz. So basically, on the basis of number of optic axis is present in a doubly refracting crystals, we can classify these doubly refracting crystals into two types. One is uniaxial crystal, another is biaxial crystal. In uniaxial crystal, we have one optic axis. Examples are calcite and quartz, while in biaxial crystals, we have two optic axes, and the example of this is topaz. So here in this discussion, we have used two very important terms. One is principal section and another is this optic axis. Now I will discuss these terms one by one. So first is optic axis. So what is the meaning of optic axis? To understand the meaning of optic axis, first we will draw a heuristic diagram of a crystal of calcite. A calcite crystal, I will draw a heuristic diagram of calcite crystal. This is, and the characteristic angles of these calcite crystals are 102 degree and 78 degree. So basically all these three faces are meeting at this point A, and at this point all these three faces are making an angle equal to 102. So basically this is a blunt corner A. At this blunt corner, three faces are meeting at this point, and all these three faces are making an angle 102 here, and at this point all the three faces which are meeting here, they are drawing 78 degree angle at this point. Now to understand the optic axis, we will draw a line passing through this blunt corner in such a way. So we are drawing a line through this blunt corner A in such a way that this line is making equal angles with all three faces which are meeting at this point. So if we draw a line which is passing through this blunt corner A and it is making equal angles with all three faces, then this is known as optic axis. This is known as optic axis for this calcite crystal. Calcite crystal. Now, another important thing about this optic axis is if we draw these two parallel lines, one line is this and another line is this. If we draw two parallel lines parallel to this optic axis, then you will find out that these two lines, they also act as optic axis. It means whenever we are drawing a line parallel to the optic axis, those lines will also act as optic axis. So the meaning of this is, this optic axis is actually not a line, rather it is representing. So optic axis is representing a direction. It is not just a line, but this is representing a direction. So what is optic axis? Optic axis is a direction. Optic axis is representing a direction. And any line parallel to this optic axis, that will also act as optic axis. Second, this optic axis is axis of symmetry. Is axis of symmetry. What is the meaning of axis of symmetry? To understand the meaning of axis of symmetry, if we go to microscopic level, then we will find out that at the microscopic level, the atomic or molecular arrangement around this axis is very much symmetrical. So due to this property, this is known as axis of symmetry, and because this is axis of symmetry, due to this reason, both the refracted rays travel with same speed along optic axis. So these are few important properties of optic axis. So optic axis is not a line, rather it is representing a direction, and along this direction both the refracted rays, means both O ray and E ray, they travel with the same speed. Another important term in double refraction is principal section. So another important term is principal section. So what is the meaning of principal section? So next term is principal section of doubly refracting crystal. To understand the principal section, what we have to do, we have to imagine a plane. So what we have to do, we have to imagine a plane that is passing through this blunt corner and that is passing through this optic axis. So we are imagining a plane which is passing through this optic axis and this blunt corner, and then we will start rotating this imaginary plane around this optic axis in such a way that it becomes perpendicular to two opposite faces of this doubly refracting crystal. So what we are doing, we are considering, or we are imagining a plane which is passing through this optic axis. We are rotating this plane, and we are rotating this plane up to the point when this plane becomes perpendicular to two opposite faces. Then at that position when it becomes perpendicular to two opposite faces, this position of this imaginary plane is known as the principal section of this doubly refracting crystal, because this crystal has three set of opposite planes, opposite faces. So basically this crystal will have three principal sections. So what we have considered, we have imagined a plane passing through this optic axis. We have rotated this plane up to the point when it becomes perpendicular to two opposite faces. Then that position of this imaginary plane is considered as the principal section. This crystal has three opposite faces, three set of opposite faces. So automatically this crystal will have three principal sections. So up to this point, I have defined doubly refracting crystals. What is the meaning of double refraction? There are two types of doubly refracting crystals: uniaxial crystal, biaxial crystals. And after this, I have defined optic axis and principal section. All these terms are very important to understand the exact phenomena of double refraction. If we draw the principal section of calcite crystal, so if this is the principal section of the calcite crystal and unpolarized light is incident on this, so here we have unpolarized light that is incident on this. Then for this calcite crystal, which is doubly refracting crystal, for this one ray we will have two refracted rays. One will move like this, another will move in another direction. In one of these refracted rays, electric vibrations will be parallel to principal section. This is known as E ray. And in another, electric vectors will be perpendicular to the principal section, and this is known as O ray. So this is E ray and O ray. So what is the meaning of this? Basically, in double refraction, we have two refracted rays, and both these refracted rays are plane polarized light. So here you have to observe this thing, that in double refraction, we have two refracted rays. One is O ray and another is E ray, and both are plane polarized light. In E ray, electric vectors are parallel to the principal section, while in O ray, these electric vectors, which are denoted by these dots, they are perpendicular to the principal section. So now we have two types of rays. One is known as ordinary ray, another is known as E ray. So what is the difference between O ray and E ray? One is ordinary ray, which is also written as O ray, and second is extraordinary ray, and this is denoted as, in short form, it can be written as E ray. So what is the difference between O ray and E ray? So first, most important difference, as the name suggests, ordinary ray, this follows laws of refraction. While extraordinary ray, it doesn't follow laws of refraction. So this is one of the most important difference between them, that ordinary ray follows laws of refraction while E ray doesn't follow laws of refraction. Second important difference is this O ray always lies in plane of incidence. While E ray in general it doesn't lie in plane of incidence. So O ray always lie in plane of incidence, while E ray it is in general, most of the times you will find that this E ray doesn't travel in plane of incidence. However, there is an exception to this. If plane of incidence is itself if plane of incidence is itself principal section, or principal section is itself plane of incidence, principal section, in that case, if this is the case when principal section is itself plane of incidence, then in this case this E ray is also restricts to move in the plane of incidence itself. It will travel in the plane of incidence itself. So what is the exception of this point? Exception of this point is if plane of incidence coincides with plane of incidence, then this E ray will travel in plane of incidence itself. Next important point is this O ray, it travels with same speed, in all directions of the crystal, in all directions of the crystal. The meaning of this sentence is there are different directions in the crystal, and this O ray travels with the same speed in all the directions. Its speed will be same. While this is not the case for E ray, while E ray travels with different speeds, in different directions, And there is one most important point, and that is, fourth point is, for E ray, these electric vectors for E ray, the electric vectors of E ray will always be parallel to the principal section. So, electric vector of E ray, they will be parallel to principal section. They will always be parallel to principal section. While for O ray, their electric vectors of O ray, you will always find that electric vector of O ray are always perpendicular to the principal section. Here, I am considering that this board is representing the principal section of this calcite crystal. Due to this reason, I am representing these electric vectors of E ray as parallel lines, parallel to this board. So, electric vectors of E ray are always parallel to the principal section, while for the O ray, direction of electric vector is like this, perpendicular to the principal section. Here I am assuming this is the principal section. So electric vector of O ray, they are oscillating like this, perpendicular to this board. So these are four important points. of difference between O ray and E ray. So O ray follows laws of refraction, while extraordinary ray doesn't follow laws of refraction. While ordinary ray always lie in plane of incidence, but this is not the case with E ray. However, there is one exception when plane of incidence and principal section coincides. In that case, this E ray will travel in plane of incidence itself. Third important point is this O ray, it will travel with same speed in all possible directions, while for E ray, this E ray will travel with different speeds in different directions. But you have to remember that along the optic axis, both O ray and E ray, they will travel with the same speed. So optic axis is the direction in which both O ray as well as E ray, they will travel with the same speed. And most important point is this fourth one, that electric vector of E ray is always parallel to the principal section, while electric vector of O ray are always perpendicular to the principal section. So this is the difference between O ray and E ray. Now I'm drawing the principal section of a doubly refracting crystal. So here I am drawing a doubly refracting crystal. This is a doubly refracting crystal. Suppose calcite, and a ray of light is incident on this, and we will draw a line at this point, a line perpendicular to this. This is normal to the interface. So because this is a doubly refracting crystal, so for this one incident light, we will have two refracted rays. One will move like this, another will move like this. Suppose this is E ray, this is E ray, and this is suppose O ray. So here we have two plane polarized light. One is E ray and another is O ray. Suppose this is angle of incidence. I is the angle of incidence. So there will be two angle of refractions, one corresponding to O ray, another is corresponding to E ray. Suppose this is angle of refraction for O ray, and this is the angle of refraction for E ray. So now in this doubly refracting medium, two type of waves are traveling. One is O ray, another is E ray. So refractive index of this material corresponding to E ray will be equal to velocity of light in free space. That is suppose c, that is represented by c, and maximum velocity of E ray in the medium, this is suppose Ve. So V is the speed of light, speed of E ray in doubly refracting medium, and this c is the velocity of light in free space. Similarly, refractive index of this doubly refracting material with respect to O ray corresponding to O ray, this O ray will observe this refractive index, and this will be represented by VO. So VO is the speed of ordinary light in doubly refracting crystals. Now according to Snell's law, this mu E is equal to sin I, angle of incidence, divided by sin RE. And for ordinary light, this will be, this refractive index corresponding to Snell's law, this will be sin I divided by sin RO. Now there can be two cases, there can be different type of doubly refracting crystals here, and there can be two cases. In one case, suppose RO, angle of refraction for O ray, is greater than RE, This is first case. There can be second case when RE is greater than RO. If RO is greater than RE, if this RO is greater, so this number will be greater as compared to this number. So correspondingly, this mu O will be less as compared to mu E. So from this formula, from these two formulas, if this RO is greater, then sin R0 will be greater, and this mu O, this will be less as compared to mu E. And when mu O is less than mu E, so come to here, if mu O is, this is less, mu O is less as compared to mu E. So from this, this mu O, this is V, this is mu O, this mu O is less as compared to mu E, and this mu is inversely proportional to the speed of O ray and E ray. So correspondingly, VO will be greater than VE. So if angle of refraction for O ray is greater as compared to angle of refraction for E ray, then this velocity of ordinary ray in the doubly refracting medium will be greater as compared to the speed of E ray in the doubly refracting medium. This type of crystals in which VO is greater than VE, they are known as positive crystals. They are known as positive crystals. So in positive crystals are those doubly refracting crystals in which speed of ordinary light is greater than speed of E ray in doubly refracting medium, and or you can say that refractive index of O ray is less as compared to refractive index of E ray. So basically, this is the condition for positive crystal. For the positive crystal, the simplest example is quartz. For positive crystals, the simplest example is quartz. So in positive crystals, velocity of O ray is always greater than the velocity of E ray, and refractive index of doubly refracting medium for O ray is always less as compared to refractive index of doubly refracting medium for E ray. So this type of crystals in which VO is greater than VE, they are known as positive type of crystals. Now come to the second case, when this RE is greater than RO, when angle of refraction for E ray is greater than angle of refraction for O ray. In this case, what will happen? If this RE is greater, then this mu E will be less. So this mu E will be less as compared to mu O. And because mu and V are inversely proportional here, so this VE is greater than VO. So there are other crystals in which speed or velocity of E ray is greater as compared to velocity of O ray, as well as refractive index corresponding to E ray is less as compared to refractive index corresponding to O ray, and this type of crystals, they are known as negative crystal. Negative crystals. So there are two types of crystals. One is negative crystal, another is positive crystal. Positive crystals are those crystals for which VO is greater than VE. Negative crystals are those crystals for which VE is greater than VO. In the example of negative crystal is calcite. So this is the case for positive crystal, this is the case for negative crystal. So these crystals, these doubly refracting crystals, they can be classified into two types of crystals. One is known as positive crystal, example of this is quartz, and for this positive crystal, velocity of O ray is always greater than velocity of E ray, while another type of crystals are negative crystals, and negative crystals are those crystals in which velocity of E ray is always greater than VO. Now question arises, if their velocities are different, then how we will draw? Now question arises, if their velocities means VO is different from VE, and here VE is different from VO. If their velocities are different, then how we will draw the wave fronts for O ray and E ray in doubly refracting crystals? So now we will draw the wave fronts for O ray and E ray in negative crystals. How we will draw? Because we will draw these wavefronts in a doubly refracting crystal. So first we will draw the optic axis of this doubly refracting crystal. Suppose this is the direction of optic axis. This is optic axis of doubly refracting crystals, and this is a line perpendicular to the optic axis. So this is a doubly refracting medium. This is the three-dimensional picture. This is the direction of optic axis, and this is perpendicular axis. If we consider a light source placed at this point, if we consider a point light source here in the doubly refracting crystal, then this light source will emit light, and because this is doubly refracting crystal, so automatically this emitted light, it will create two type of wavefronts. It will split into two type of light. One is O corresponding to O ray, another will be corresponding to E ray. So we will have two type of wavefronts, one corresponding to O ray, another corresponding to E ray. First we will draw the wavefront for O ray. You are well aware that for O ray, speed remains same in all possible directions. So the O ray which is emitted from this point, it will travel equal distance in equal time. So in three-dimensional picture, this point source in doubly refracting medium, this will emit a spherical type of wavefront for O ray. So in two-dimensional picture, it will be like a circle, but in actual practice, this will be a sphere. Why this is a circle in two dimension? Because it is traveling equal distance in equal time. These are equal distances in equal time. O ray travels with the same speed in all possible directions. So due to this reason, it will travel equal path in equal time. So automatically its wavefront will be spherical in three dimensions, while it will be a circle if we plot this wavefront in two dimensions. So this is the wavefront for the O ray. So this is the wavefront for O ray. Now we will draw the wavefront for E ray. Now we have to draw the wavefront for E ray, and we are drawing these wavefront in negative crystal. In negative crystal, the speed of E ray is always greater than VO. VE is greater than VO. So automatically wavefront of E ray will always move ahead as compared to the wavefront of O ray. Or you can say wavefront of O ray, it will lag behind as compared to the wavefront of E ray. But one important thing you have to remember, that both O ray and this E ray, they travel with the same speed along the optic axis. So in this direction, in the direction of optic axis, they will travel equal distances in equal time, because their speeds are same in this direction, either in this direction or in this direction. Their speeds will be same. So both these wavefronts will touch each other at this point. And in other directions, the wavefront corresponding to E ray will move ahead. And this will be the two-dimensional picture of this wavefront. in 3 dimension, this is the wavefront corresponding to E ray in 2 dimension. This is an ellipse. If we talk about 3-dimensional wavefront, then it will be a ellipsoid type of structure. So in negative crystal, the wavefront for O ray is a circle in 2 dimension and it is a sphere in 3 dimension, while the wavefront for E ray is ellipsoidal in 3 dimension and ellipse in 2 dimension. And you have to remember one thing here, that in negative crystal, this spherical wavefront always lie inside this ellipsoidal type of wavefront. So this is important to remember, that this spherical wavefront always lies inside the ellipsoidal type of the wavefront in negative type of crystal. From here you can also observe one important thing, that along the optic axis both E ray and O ray, they are traveling with the same speed, but along the perpendicular axis this E ray has maximum speed. E ray has maximum speed along the perpendicular axis, and along the optic axis it has minimum speed in negative crystal. So these are the wavefront of O ray and E ray in negative crystal. If we talk about positive crystal, now we can talk about positive crystal. How can we draw the wavefronts in a positive crystal? In positive crystal, so in this positive crystal, suppose this is the optic axis, this is the optic axis of this positive crystal, and this is perpendicular axis. This is perpendicular axis. We placed a source here at this point. In doubly refracting crystal, this will emit light, and this emitted light, it will convert into two type of wavefronts. One is corresponding to O ray, another is corresponding to E ray. For O ray, first I will draw the wavefront for O ray, because O ray travels with the same speed in all directions. So this wavefront will be a sphere, or you can say this is a circle in 2 dimensions. So we can represent this as a circle in 2-dimensional case. So this is the wavefront for O ray. Again, now in positive type of crystals, what we have in positive type of crystals, VO is greater than VE. In positive crystals, VO is greater than VE. It means velocity, so velocity or speed for E ray is always less than VO, except the optic axis. So along with optic axis, both these wavefronts will touch each other, but in other direction, except other than this optic axis, this O ray will travel faster. So automatically the wavefront for E ray will be an ellipse like this. This will be an ellipse like this. So now velocity of, or the speed of O ray is higher, so it is moving fast, and speed of E ray is less, so it is lagging behind as compared to this, the wavefront of O ray. So in positive type of crystal, you can observe one thing, that this ellipsoidal type of wavefront for E ray always lies inside the spherical type of wavefront for O ray. So ellipsoidal type of wavefront lies inside the spherical wavefront for the positive crystal. And here you can remember one thing, that along the optic axis, speed of E ray is maximum along the optic axis. So in negative type of crystal, speed of E ray is maximum along the optic axis, while it is minimum along the perpendicular axis. While in case of negative crystal, it was opposite. In case of negative crystal, E ray has maximum speed along the perpendicular axis, while in positive crystal, this E ray has maximum speed along the optic axis.